Yeah, so it's 7 o'clock now. So let us begin with today's class. So today we'll be mainly dealing with the week 9 contents, okay, which is based on numerical solutions for 1D Euler equations. And this is particularly for the course of Introduction to CFD, which is AE20. So I am Sumant Morav. I am a PhD research scholar in Department of Mechanical Engineering at IIT Bombay, and currently these tutorials are going in two sessions. One is the Friday one, which is this present session. Along with that, the other session will be on Sunday. Okay. So in week 9, the contents were mainly based on solution to one dimensional Euler equation. But before going into one dimensional Euler equation, the linear advection scheme, which I can just write it as dou u by dou t plus a constant, which is sound speed, into dou u by dou x was equal to 0. This we had discussed earlier also. Why we are bringing it again here is that the Euler equations which we will be going to discuss are similar to this linear advection scheme, but in the sense that they are non-linear. Okay, so in this particular equations we had seen different numerical schemes also and how they work out. Also we had implemented a simple code to in order to see whether the solutions which we are getting are correct or not. And what we saw in general for these kind of equations is that the equations which used a kind of upwinding scheme, either a first order upwind or a second order upwind, those kind of schemes were found to get provide much better solutions. That is, for example, if we had considered this A to be positive, that is sound speed that is propagating in positive x direction. In these cases, which we saw that the backward difference scheme, that is the FTBS scheme, forward time and backward space. So those particular kind of schemes gave a better results because we were considering the influence from the previous grid point and not from the next grid point. Okay, we were not taking the influence of the eth grid point. So we saw that these kind of schemes were quite stable and gave good results also. Okay, so also we saw some other schemes like Lax-Ventropf scheme, wherein using Taylor series the uh, the scheme was obtained. Okay, so in the Euler equations are mainly our Navier-Stokes equation only, which we saw in the last class. But there is a difference. Can you write down on the chat box what was the main difference between the, say, 1D Navier-Stokes equation and 1D Euler equation? Do you know the difference? There is only one difference which exists. Okay, yeah, viscous. So Euler equations are mainly for inviscid flows. The problem is that although these equations look very simple, I mean, if you consider full-fledged 2D, like even 1D Navier-Stokes equation, you have something like dou u by dou t, plus you have advection term also. Okay, u dou u by dou x. Then you have some pressure term also, which somehow you get the solution for using the mass continuity. Then you have say the viscosity into del square of u. You have these many terms. So these term mainly cancels out, and if there are no pressure forces, even this term is not present. Okay, in our Euler equations. So in a way, these Euler equations, if you look at it, they are very simple. But when we go on to numerically implement them, they have lot of challenges. Mainly two categories are there. that is dissipation and wiggle kind of solutions, okay, which you get, okay. So dispersion it is called as. And basically what happens is that due to presence of this viscous term nu, uh, the solution is naturally dampened out, okay. I mean, you can imagine it in a physical sense that due to the viscosity which is present, the initial sinusoidal wave can reduce its magnitude over a period of time, okay. But this is not allowed, okay. This is not allowed in this Euler equations because there is no viscosity which is involved, okay. So we, for example, if we have a very sharp kind of initial solution, okay, this sharpness needs to be maintained, okay, in the final solution also, whereas it was not required when we had this viscous term, okay. So the solutions can be dissipated, but this is not allowed with respect to Euler equation. So that is why Euler equations are numerically challenging, okay. They are, I would say, numerically challenging because you have to come up with a very good scheme to solve these kind of Euler equations. So mainly in the contents, first we saw like how we can arrange it in a flux based format. That is, you have basically three equations, right? One is for the mass conservation, momentum conservation, and the energy conservation. And in energy conservation also, we do not consider the thermal conductivity, which is like a viscous force only for the energy equation, okay. So there also we do not consider the thermal conductivity. Ignoring that, what is the energy equation, we write it down, okay. So that is the energy conservation. So we had three equations, and basically we categorize these equations into like three different variable parts. So in the first part we had mass conservation, where we had dou rho by dou t plus say dou by dou x of rho u is equal to 0, okay. So otherwise you can write u into dou rho by dou x also, okay. So what happened is that we took this as one variable, say u1, okay. Just we arranged it. In the second we had dou by dou t of rho u, okay, in the transient term, okay. We took this as say u2, and in the energy also we had rho e total, okay. We took it as u3 variable, so as to arrange it in some kind of matrix format and see what are the characteristics of this equation, so that before solving only we come to know which numerical scheme we have to use, okay. So that was the main agenda behind considering making all these things, mathematical things, like I mean, calculating the Jacobian, which you have seen in the weekly contents, using these equations, and then doing the singular value decomposition to obtain the eigenvectors, the eigenvalues, okay, and using the eigenvalues you calculate what is the characteristic direction of propagation. Through that you understand which scheme you have to use, okay. So that is the main intention behind doing all these mathematical activities, okay, I would say, according to what I have understood. So that was the main intention behind doing that I mean the mathematical stuff, okay. Ultimately we have to try to understand which numerical schemes are more stable and all, okay. So that was one thing, and then finally when we did all those things, we like converted into two forms. One was like say dou into, let me write it as u bar by dou t plus dou by dou x of f bar, okay, is equal to 0. This was one form which is called as flux form mainly, okay. Then the other form was in terms of the Jacobian, where you wrote as dou u bar by dou t plus a into dou u bar by dou x, okay. This is u bar, okay. It consists of u1, u2 and u3, okay. So this is equal to 0, and then you kind of found out the eigenvalues of this particular matrix, Jacobian matrix. Fine. So that was a thing. So once you found out and saw which kind of schemes kind of fits, okay, better, Then we had mainly two approaches to solve these 1D Euler equations. Okay, and one was quite, I would say, an easier technique according to me, is the flux based approach. Okay, what you do here is that you write the equation in this term in the flux form. Okay, so then say you can just say write it as explicit time marching, wherein you can say u bar n plus 1 minus u bar n is equal to minus of dou f bar by dou x at say n. Okay, that kind of things you can do. You had lax Ventrov scheme also, which was more stable. Okay, so that was a good thing. In the wave splitting approach, it's a bit complicated. For that, again, we have to come into the characteristics. Okay, we have to see whether the we have to analytically predict. It's basically analytically predicting in which direction the wave will go, or what will be the characteristics of the solution. Okay, so based on that we can split it into two parts, and for the two different parts we can apply two different schemes like FTBS for one part and FS for one part. Okay, and then we can solve it. So that is again quite a mathematical procedure which is required. But anyway, flux based approaches are also found to give good results. Okay, so anyway, so that was the brief overview, I would say, of the things which you have learned. And so based on your request, so mainly I'll try to first solve a simple vorticity stream function based formulation, where I'll just try to show how we can write a code for solving vorticity stream function equation. And then we will try to apply it for a simple lid driven cavity problem, which we had discussed in the previous week. Mainly the formulation for vorticity stream function, we had discussed it in the previous week. The formulation we had discussed, but the solution methodology we will discuss today, and we will see a sample case, that is a lid driven cavity problem. And I'll just explain the code, and then maybe I'll attach it with this slides also, so that you can also try to run it and check the results. Okay, so let me just briefly go through that problem statement and the solution methodology. Okay. Okay, are you able to see these equations? I mean the slides. Okay, thank you. Yeah, so these were the two equations which we discussed for vorticity stream function, and why I am starting with vorticity stream function, although you had asked for simple algorithm, I remember. See, always we have to take baby steps. That is what I feel, especially in CFD. Okay, uh, this has been my training also. In, if I tell personally, you have to start with some simpler problem, okay, or simpler formulation. Try to get solution for that. Okay, then you can march to a uh, slightly complex thing. Okay, so in this week I am planning to teach this, the vorticity stream function coding. Okay, in the next week I am planning to explain about the simple algorithm and probably show you a code. Okay, so the vorticity stream function which we like saw, formulation which we saw in the last week. Okay, um, it was these two equations mainly, which I have marked it with blue color. Okay, so one is the transient expression for the vorticity, that is this dou omega by dou t plus the advection of vorticity and the diffusion of vorticity. Okay, so you can clearly see that the pressure has been removed out of the equations, which is very good for us. So we have here only vorticity, okay, and we have velocities also. Okay, we don't have anything else, we have only vorticity and velocities. And when we do the time stepping, we can do in such a way that we take the velocities from the previous time step. Okay, we can take the velocities from the previous time step. That is the strategy which is used. So then we are left out with only one variable omega. Okay, so that we can directly solve for omega. So in this way we will get the solution for omega. Okay, but to calculate velocity in the previous time step, we need to know the value of stream function. Okay, stream function will only help us to get the value of velocities. So along with vorticity, we also have to calculate stream function. Okay, that is the requirement. Okay, so the stream function equation is something like a your Laplace equation. It's not exactly Laplace equation; it's a Poisson equation actually. So it's del square psi is equal to minus omega. Okay, so this particular equation you need to solve. Once you get the know the value of omega, you can try to get the value of stream function. Initially, we will assume that velocities are zero. From that, we will get omega. Okay. Now, once we get omega, we will get psi. From the value of psi, that is the stream function, we will calculate the velocity at our first time step. That is u is equal to d psi by dy. Okay, v is equal to minus d psi by dx. Using these equations, we will get the value of u and v at the first time step, which we will use for second time step to calculate omega. So I hope that that is understood, the solution methodology. Okay, so that is the solution methodology which we use, and these vorticity stream function approach is a very good approach, I would say, if you are solving only 2D problems. Okay, you can take any 2D problem, okay, any grid, anything. Okay, if the problem, the nature of the problem is two dimensional, then the stream function vorticity is the best thing which you can do instead of going for simple algorithm and all those things. Okay, definitely that is helpful for 3D flows and all, but I would say if the flow is 2D, go with vorticity stream function only, because coding wise also it is simpler. Okay, and you will not get confused with all the staggered grid and all those things. Okay, so that is my suggestion. Okay, if your problem is 2D, okay, but if you have it in the back of mind that you want to extend it to 3D later on sometime, okay, then again you have to use simple algorithm or some other algorithm only. Okay, but if you want to do only 2D, then this is the best thing. Okay, so I hope that the solution methodology at least is understood. Okay, first we calculate omega by using the values of velocity and the previous time step, and then we calculate the stream function to update the velocities using these relations, and then we go to the next time step. Okay, fine. So that is the solution methodology. Okay, and let us try to discuss the problem statement which we will be trying to attempt with this solution methodology. Okay, so we will be trying to solve the lid driven cavity problem. Okay, so in this particular problem, it is an industrially relevant problem also. So what happens in many of the paint manufacturing or industries is that we need to mix two different substances very efficiently, and in that time the fluid two different fluid, you can say, in this case we will consider only one fluid, or fluid and some particles are put in a cavity, and a conveyor belt is moved on the top. Okay, so with a constant velocity, say. Okay, so that will make these fluid particles to mix with the chemical powder components or something like that. Okay, very well, and then we get a good quality of the product whatever we want. So this particular problem involves a cavity inside which there is a fluid flow which is happening. So initially the flow is stagnant. Okay, so but what we do is that we move the top wall with a constant velocity u. Okay, all the other three walls are stationary in nature, that is their velocities are zero. Okay, Now we want to try to understand at the steady state how the flow pattern will reach. What will be the flow pattern? Okay, so if we are moving the top wall with a varying velocity, say for example sinusoidal velocity if we are giving, okay, so in that case the solution will not reach a steady state, it will actually reach a periodic steady state. Okay, so that's a different thing. We want to try to solve for steady state, we are assuming a constant velocity. And the other thing which is very important to note is the boundary conditions for this particular problem. Okay, so for psi, that is stream function, boundary conditions are very simple. You have say on the vertical walls you have u is equal to 0. Okay, that is a left and right wall, you have u is equal to 0, right? So then d psi by dy will become 0, but it is already a vertical wall. D psi by dy is equal to 0 means that psi needs to be constant. Okay, stream function has to be constant. Okay, so which means that it's constant along the left and right wall. Similarly, along the horizontal wall also you will observe that psi needs to be constant because d psi by dx is equal to 0, and it is already a horizontal wall. Okay, so psi needs to be constant. We assume that the stream function will be 0. Okay, it can be any constant. Okay, it doesn't matter, but in this case let us assume it to be 0. Okay, 0 along all the walls. It is a constant value along left and right, top and bottom, we assume it to be 0. Okay, so that is the boundary condition for the stream function. Now for vorticity it is a quite a bit involved. Okay, so what happens is that we have on the walls we have uh, the vertical velocity to be 0 on all the walls. Okay, not only restricted to horizontal or vertical, for all the walls v is equal to 0, y velocity. Okay, which means that d psi by dx is equal to 0. So if I consider the left wall for example, okay, let me just consider left wall, d psi by dx is equal to 0. Okay, at this particular point 1. Okay, which is the left wall. Okay, so using the Taylor series I can write the expression for the uh, grid point which is adjacent to the left wall, that is 2, using the Taylor series in terms of 1. Okay, in this manner psi2 is equal to psi1 plus d psi by dx plus d square psi by dx square. Now since u is also equal to 0 along that particular wall, you can take it to be constant also. On the left wall it was 0, you can take it to be c which is on the top wall. Okay, 1 value. Okay, then d psi by dy will become 0 or 1. Okay, based on which wall you are taking. Okay, then whatever it is, d square psi by dy square will be 0 only. Okay, even if d psi by dy is constant. Okay, so we just substitute it in these particular equations. Okay, d square psi by dy square is 1 in this particular omega equation. You will end up with only d square psi by dx square is equal to omega. Okay, so here in d square psi by dx square you substitute omega, that is what is done here. Okay, and then we can basically write this omega, and you know that d psi by dx also is equal to 0, that you have come from v is equal to 0. So d psi by dx is 0 and d square psi by dx square is came out to be minus omega. So omega you can write in terms of stream function. Okay, so this is for left wall. Okay, similar things you can do for the right wall, top wall and bottom wall also. Okay, so I hope that the implementation of boundary condition is understood. Okay, so I will share the reference link. Okay, you can go through this to understand the boundary conditions if you are not understood. Okay, so basically we use a combination of the Taylor series and the Poisson equation to calculate the boundary condition. Okay, till here is this are these points clear? The solution methodology and the problem statement and the boundary conditions. Are there any questions with respect to these three things? If there are no questions, okay, let me just try to show you the program and then we will try to run it. Okay, but okay, this is the program which I had written. Okay, but before explaining, I'll just run it, okay, because running will take some time. So while it is running, we can explain the code, okay. Just go to command prompt. Okay, I have come to this particular folder. Hmm. Now the way in which we compile the C program is as follows. Like we use a GCC compiler. Okay, then the file name minus I have to create an output file name also, LDC, which I'll write. You can write anything. You can write this as output also. Okay, and I'll link it with some mathematical libraries, LM. Okay, that is a mathematical library. Okay, so it is compiling the code now. Okay, it is telling me that there is some error with my code. So let me just see, I did some modification. So e raised to minus 3, 192 e raised to minus 3, I think I'll write 1 into e raised to minus 3. Okay, okay, now I think it has compiled quite successfully, and it creates an executable file, okay, output, named as output. Okay, so just let me run the output file then. Output, just output. Okay, it will start running and it will finally give us results, but in the meantime, okay, let us try to see the code also. Okay. Mm. Okay, so first thing is you have to define the parameters, the length of the domain and the number of grid points which we have to select and all those things. Okay, fine. So the number of grid points along x direction and y direction, I have kept it very low, okay, so that we get quick results. Just 30 points, and length, it was given in the problem statement, point 0.1 and point 0.1. Reynolds number I think was 100, so that is why I have taken the viscosity to be 10 raised to minus 3, because Reynolds number is 100 and length is zero point 0.1. Okay, so based on that the viscosity I have defined. Okay, so anyway you have to define these variables. The important variable is this del x. Okay, let me just zoom it. Okay, this del x and del y. Okay, so we are taking a uniform Cartesian grid. Okay, this is collocated grid only, we can solve it in a collocated grid. Okay, so del x del y will be nothing but length along x divided by nx minus 1 and ly minus 1. So this is how we define the geometric parameters. The first thing which we have to define is the initial values of u, v, omega and stream function. Okay, these initial values are very very important. Without these you will not get a proper solution. Okay, because you see, if everything was zero you will not get any solution. Somewhere something is happening, that is why you are getting the solution, right? I mean some positive values or negative values, some values. So that has been initialized here, that if j is equal to ny minus 1, okay, you say that the velocity is 1. Okay, so you know that the y index is j. Okay, keep this in mind, y index is j as in the class material also, and the x index is I. Okay, and we have a uniform Cartesian grid. Okay, with nx cross ny points. Okay, and nx and ny are both same in our case. So here I am just drawing a 4 cross 4 cell. Okay, so nx here will be actually 5. Okay, nx and ny will be 5. Okay, so number of points are 5, 1 2 3 4 5, right? So there will be 5 points in y direction and x direction also. Okay, but the number of cells, if you see 1 2 3 4, you have 4 cells. Okay, so that is the way in which we do. Okay, here we have just used the finite difference method. Okay, now don't get confused with finite volume. Here we are not using a finite volume method. Here we are just using a finite difference method. Okay, you can use finite volume also, but then the things will become more complicated in that case. Okay, you will have the grid points, number of grid points 7, and you will have only 4 5 cells and something like that. Okay, but here we'll just consider finite difference method. So each and every this corner point is the cell centroid for us. Actually, there is no concept of cell, first of all. Okay, so it is just this way. Okay, I hope that this is clear. uh, where was I? So I have initialized at the top wall velocity of 1. So we need to enter the time marching. Okay, this is the time marching step. Okay, so I have started to go over the time loop now. So I'll go over this time loop whenever I reach a convergence tolerance, that is say omega at n plus 1 minus omega at n, if this value comes out to be less than some epsilon value which I have defined it to 10 raised to minus 3. Okay, absolute. Okay, absolute you have to take, very important. Absolute of this difference between two time steps, when it comes less than some epsilon value, then I will stop the code. Okay, so that is why I have written this while loop. Okay, so that is how it works. And first, as I said in the solution methodology, first I am trying to calculate omega values. Okay, so omega, so basically I'll just write it on a code here. So omega new, w new, what you found out was omega old, right? Plus the advection term. Okay, so you add the advection term minus u into omega x d omega by dx, you had minus v into dou omega by dou y, you had, right? And then plus you had diffusion term, viscosity into del square of omega. So that is what I have written here. Okay, just don't get confused. I have first written the diffusion term nu into del t into omega xx plus omega y by d square omega by dx square plus d square omega by dy square minus this whole thing. Okay, and then I have calculated it previously using the second order central difference scheme. Okay, so this is how I find out omega on all the grid points except the boundary grid point. Okay, so this is very simple, right? I mean, it's just you take the all the grid points in the internal grid points, okay, in the domain, and then just calculate omega. This is very fairly simple. I mean, there is no Gauss Seidel or something involved in this. Okay, so this is how we calculate omega. So now the second thing is to calculate psi, which requires the iterative methods. Okay, because we have a fairly complex equation. Okay, actually here also we could have used Gauss Seidel and all, but I have done just explicit time stepping. Okay, so that is why I did not have to use those complicated things. Okay, so the next thing is just we have to say dou square psi at n plus 1, okay, divided by dou x square plus dou square psi at n plus 1 only divided by dou y square is equal to minus omega. Omega at n plus 1 we have already calculated in the top loop. Okay, so this equation we need to solve here. Okay, I am just using the Gauss Seidel method, which you have learned already. Okay, um, I hope that this is clear. Like the the coefficients, they have been obtained, like, see, psi nu, what I am writing it as. Okay, uh, into you will get AP terms, which involves the AP terms mainly involve 2 by del x square plus 2 by del y square if you write them down. So if you have a very uniform grid, then it will become just 4. Okay, this divided by 4. So basically average of all the neighboring psi values divided by 4 if you have a very uniform grid. Okay, so that is how you calculate psi, and then you have omega also on the right hand side, which you have to include. Okay, Then when you calculate psi, once you calculate psi using the Gauss Seidel method, you calculate the u at that particular time step, u and v. Okay, and very important is the implementation of boundary conditions, which I had discussed previously. So this is how you kind of implement the boundary conditions uh, using the indicial notation. Okay, the equations I have discussed previously. So once you implement the boundary condition, as I told earlier, you need to calculate the error, okay, between the previous time step and the new time step, which I have written here. Okay, this particular error that is being calculated in this particular step. Okay, once you calculate the error, I am just printing the error to see the convergence at different time steps. Okay. So once the error, this max error, it goes below 10 raised to minus 3, the code stops. Okay. We have reached the steady state. You can take it to be 10 raised to minus 6 also. It will take too much time. Okay. But you will get more accurate solution. Okay. And then finally you can print it to a file to do the visualization. Okay, so this is just the standard printing format which we especially use in C language. Okay, based on your language you can take anything. Okay, so let us see what has happened to the code. It has converged. Okay, so you can see that within 900 iterations itself, the error went below 10 raised to minus 3. So at the 900th iteration, we had an error of 0.001. Then 1000th iteration it did not go because the error might have gone below 10 raised to minus 3. Okay, so that is why it has stopped. Now we will try to visualize the results. Okay, using post processing software. We usually use the paraview. Okay, so whatever data file I have written, I have to also visualize the flow, right? And then I have to calculate the values and then see, compare with the literature and all those things. Okay, so for this post processing we usually use the paraview, which is an open source software. Okay, so can use that also. So you can just open this results.dat. So I had written it, the final results in this results.dat file. Okay, so now you will be able to see the grid. Okay, you can see that it's a very coarse grid, it's a uniform computational domain. Okay, and if I say data access grid, okay, B it's not showing. It's a zero point 0.1 cross 0.1 domain. Okay, now I'll just go to, say, click on U. Okay, which will just show me the x velocity contours. Okay, so this is how it looks, and then you can take the data over this line and then compare with the literature. All those things you can do later. Okay, so I hope that this coding aspect is clear. Okay, so are there any queries with respect to this, with this coding aspect? Now we can move towards the question and answers. Okay, are there any queries with respect to the code which we have seen and then the solution methodology? Okay, if there are no queries, let us move to the problems. Okay, let us do some couple of problems. So in the question number one, we have one-dimensional Euler equation, okay, which is given by this in the flux format. It is given here. Okay, you can get to know that it is dou u by dou t plus dou f by dou x equal to 0. It is the flux format in which it has been given. The element f3 of the flux vector f is equal to, how can it be written in terms of the conserved variables? So that is the main equation. Okay, so first we have to try to see what is this F3 in terms of your density, velocity and energy. Okay, so that is the first thing which we have to see in the Euler equation. This F3 I think will come mainly from the energy equation, right? So yeah, F3 will come from energy equation. So you can write down the energy equation. Try to give some assignment on course grid to two iteration. In to solve on pen and paper, you are telling? Yeah, maybe I'll see if there are any problems. As of now, I cannot formulate it because I think it will become too complicated to do this on pen and paper and all. Okay, but let me see if there are any problems. I'll try to bring it up. Okay. Um, Anyway, see, what I think is that whenever you do coding, na, I mean, this pen and paper thing will be helpful, but you need not solve it, okay, on pen and paper values first and then write the code. You need to write the loop and all those indices correctly on the pen and paper first, okay. Then you can go for code, okay. So you need not get the values on pen and paper and then write code, okay. So usually what we do is that we make an algorithm of how to solve the step by step procedure, and then once we make that step by step procedure, I'll write the loops also, okay. For I is equal to this solve these equations, okay. So this I already know, I'll solve that, okay. So then go to the next step, do this, finally you check for convergence, okay. So then finally you write down the data, okay. And then in between you need to have some convergence checks also, okay. So like for every 100th iteration I had like printed the data, you saw that, okay. So in order to see if the solution is converging or diverging, usually solution will diverge, that is you will get some infinity results if your time step size is very large, okay. If you have like current number greater than 1, because we are using explicit time stepping here, okay. So okay, so that is with respect to the question which was asked, okay. So in this, let us try to see the energy equation first, okay. So this is in general all the three equations combined I have written, okay, in single equation only. Mainly you will get F3, okay. Mainly will get F3 in this energy equation, dou by dou t of rho et plus dou by dou x of rho et plus pu is equal to 0, which is the energy equation. Here you will get u3 and f3, okay. This is termed as f3. Now if I write f3 separately, I'll write it down. F3 is equal to rho et plus p into u. See, we have taken rho into et already as u3, okay. Rho into et I know already. So what is the question is to express this f3 in terms of u1, u2 and u3. We have f3 in terms of energy, pressure and velocity, okay. So I have to convert this into u1, u2 and u3. That's the agenda. So rho into et I already know it as u3, okay. um, then u also I can write it down as just u2 by u1, right? Because u2 is rho u and u1 is rho. So rho u by rho will be u. So that is why u I can write it as u2 by u1 only direct. So I know rho et also, I know u also in terms of u1, u2, u3. Only remaining is pressure term, okay. So this is the main thing which we have to solve, okay. We don't know how to express directly pressure in terms of u1, u2, u3, okay. So we have to do some calculations here. So usually the energy can be expressed in terms of this pressure energy using this adiabatic equation. This mainly comes in thermodynamics, okay. So mainly you can write it as E is equal to P divided by rho into gamma minus 1, okay. And then what you can do is that this E is nothing but the mainly the I mean, I think the potential energy which comes due to pressure. I mean, you can express it as total energy minus the kinetic energy. Okay, E you can express it that E total minus kinetic energy is equal to this particular part. Okay, now you can express P. Okay, in terms of these all these things, you can clearly see now that okay, E total I can express it. Okay, E total I can express it as you have rho also, rho into E total, again you can express it as u3 u, you can express it as u2 by u1. So in general you are expressing P now in terms of u1, u2 and u3, okay. So finally you have got P also in terms of U1, U2 and U3. You can sit and try to do this. Okay, I'm just giving an idea of how you can solve this problem. Okay, so finally I express P also in terms of U1, U2 and U3. Other two things I just know already. Okay, then I just substitute everything. Okay, rho Et into U plus P into U I have. U I'll just take it common outside. U2 by U1 I'll express U as U2 by U1. Rho Et as U3 I have expressed it here. Okay, then you have P. Okay, P I have found out here. Okay, so then you can just do some manipulations and come up with the final equation. Okay, so if you compare it with the options which you have in this, so it compares well with which of the options, option number D. Okay, so option number D, that should be the correct answer for this question. Okay, question number 2 is also continuation of question number 1. Okay, just hang on for a second. In this question they have particularly asked us to um, calculate the df3 by du1, right? See, it is very simple. We have already calculated the value of f3. Okay, in the previous question. Okay, so only the thing is we have to differentiate with respect to u1. Okay, so that's the question which is asked, I think. Yeah, so let me come up from the previous answer. So in the previous question I have got this answer for f3, which I can express it in terms of u2, u3, u1, u1, u2, u3, whatever it is. Okay, this I had got previously. Now I just differentiate with respect to u1. Okay, so this u1, it will become minus 1 by u1 square, all the other terms remaining same, and here I had u1 square, so that will become minus 1 upon u1 cube, and minus of minus, it will become plus, so I have written just plus directly here. Okay, so you will directly get this equation wherein you will have, instead of u1 you will have u1 square, u1 square you will have u1 cube. Okay, so that is the basic differentiation. Now if you compare it with the options, okay, you will see that uh, which of the option number D should be correct. Okay, so are there any other possibilities? So if you see the options, option number D should be correct. A and B are anyway incorrect. Gamma minus 1 by 2 has come. Okay. Yeah, C should be also correct. Okay, correct. You are correct. So why? Because we can express this u2 by u1 as u. Say, okay, we can express this u2 by u1 as u, and then u3 by u1, u3 we can express as rho at, and u1 we can express as rho. Instead of that, what you can do is that you can express all these in terms of basic terms. Okay, like u3 as rho at, u1 as rho, okay, u2 as rho u. Okay, you just express it, because here in this option number C we see that in terms of primary variables the option is given. Okay, here it was the calculated u1, u2 and u3. Okay, so here it has been given in terms of primary variables, so you can convert them back into primary variables. Okay, directly substitute what are the values of u1, u2 and u3. u1 is equal to u, u2 is equal to rho u, u3 is equal to rho et. Just do that substitution and you should be able to see that option number 3 is also correct, that is option number C. Okay, so I hope that that is clear. Okay, So the third question is the eigenvalues of our Jacobian matrix. So this is again formed by the elements of that flux matrix. Okay. So basically, no, sorry, this is used for way of splitting approach. So here we tend to write the equations something like this, I think. Mm, so we tend to write dou u by dou t plus a into dou u by dou x. We need to have this dou u by dou x, keeping it constant, like that is the main agenda here. Okay, so this is the way in which we come up with this values of a. Okay, and this a values are, I think, got by doing dou f by dou u only. Okay, so these values are anyway got, and we get some matrix wherein we have this dou f1 by dou u1 and f1 u2 f1 u3, and in the second row we have f2 u1, something like this. Okay, when we all calculate this, okay, we finally come up with the expression for a. Okay. Okay, so I have also not derived the expression for a, but that is the way in which the expression for a is calculated. You kind of do dou f1 by dou u1, dou f2 by dou u2, dou f1 by dou u3. I think it is given in the class materials. Let me just look over it. It is derived in the class material, if you can see. Okay, the derivation has been done, so that is why I did not do. It will be just repetitive action. Okay, so dou f1 by dou u1, you can see that it goes to clearly 0 because f1 is nothing but u rho into u, you get it as. Okay, we have done this exercise just now. Okay, f2 also you get it as rho u square plus p, which you expressed in terms of u2 and u1. f3 we have expressed in the first question. Okay, so dou f1 is nothing but u2, so you will get 0 1 0. Okay, in the first row. Similarly, you know the expression for f2 in terms of u2 and u1 u3. Okay, so you just do this dou f1 by dou f2 by dou u1, all these things. Okay, these are given in this class material, you can see. Okay, and then you will finally end up with this a matrix. Okay, now what you can do is that you have to find out the you have to find out the eigenvalues, right? Yeah, sorry, you have to find out the eigenvalues. So basically you have determinant of a minus lambda into I is equal to 0, and that is how you find out the values of lambda. Okay, so is that clear, the derivation? See, this might look complicated, this determinant of a minus lambda I is equal to 0. You can work it out on pen and paper. Otherwise, there is a software named as Mathematica. Okay, I think in MATLAB also it is possible. Symbolic expression solution is possible. In Python also it is possible. I know that. Okay, you can solve it using these softwares also. Okay, so is that clear? The derivation. One option is pen and paper, that I think would be complicated. You can go with a Mathematica software wherein you can write the symbolic expression and say I want to find out the eigenvalues. The third option is MATLAB symbolic expression, you can get the answer, and Python also you can get. Otherwise, the last option is you can see some online tools also. There are some online tools also, I think, wherein if you write the metrics in symbolic forms, you can get the symbolic answer. Okay. Okay, I have tried in Mathematica. Okay, maybe in the next week I'll try to do it in MATLAB. I don't have Mathematica. I'll try to do it in MATLAB or some online tools and just show it. Okay. Mathematica, my friends had tried, I think, some similar things. Okay, did not get any solution, some result in root form. Okay, let me just see through that. I'll let you know how to get the answer for that. Okay, but in general, that is the procedure, and finally you get the values of lambda as u plus a, and u minus a. Okay, so the option number, what is that? Option number C should be correct. Okay, so then this is mainly on wave splitting approach, I think, which will be covered in the Sunday lecture. Okay, but I'll just introduce it. Okay, we are running out of time. Okay, so if the Jacobian matrix A is split as say A plus and A minus based on this direction of propagation. Okay, now given it is given that the flow is supersonic, in that condition, which of the following should be correct? Okay, so what do you think should be the correct answer? So basically we split it based on the values of lambdas, okay, whether the lambda, that is the eigenvalue which we saw in question 3, whether it is going positive or negative. Based on that, we determine a plus and a minus. Okay, for lambdas which are going positive, we put them in the a plus bracket, and then the lambdas which are going into negative, for those eigenvalues, we put them into a minus matrix. Okay, so that is the way in which it is done. So given that the flow is supersonic, u is much greater than a, sorry, u is greater than a, not much greater than. Okay, it is just greater than a. Okay, so if you see lambdas, then you will find out that if the uh, uh, what is that, sound speed, if you take it as positive. Okay, so which is in general the case. Okay, you will find that the all the lambdas are going into positive region. Okay, because u is greater than a, and so you have all the lambda 1 minus, lambda 2 minus, and lambda 3 minus, you all have it to be 0, because lambda 1 plus is equal to lambda 1, lambda 2 plus is equal to lambda 2. Only positive values are there, right? There are no values in the negative bracket. Okay, so that is why you see that f plus will be equal to f, and f minus will be equal to 0 only. Again, similar logic as that of lambda. Okay, so that is why you see the way in which you calculate a plus is df plus by du. Okay, so df plus, we already know f plus is f. Okay, so then it will just become df by du, which is nothing but again a only. Okay, because a is actually dou f by dou u, we write a plus as dou f plus by dou u. Okay, so again we get a plus is equal to a only. Similarly, a minus, we get it to be 0. Okay, so I hope that these things are clear. Okay, the remaining questions, the remaining 5 questions, I think they will be solved in the next class. Okay, so mainly they will be on, I think, the flux based approach to solve the Euler equation, and then the wave splitting approach. Okay, I have tried to cover the calculation of this Jacobian matrix, and then the eigenvalues. Okay, so that I have tried to do. Okay, so I hope that this is clear. Okay, if there are no other queries, we can leave. Okay, so question number 5th was mainly on the derivation of Lax-Ventov scheme. Again, it is quite a bit involved. It will take some time, so I will attach this. Okay, in the Google Drive. Okay, maybe you can have a look at it. I have tried to derive the Lax-Ventov scheme for 1D Euler equation, which was asked in the question anyways. So mainly you have to do it in 2 steps. I'll just briefly go through how the way in which we derive the Lax-Ventov scheme. So as I told earlier, the Lax-Ventov discretization is mainly derived from the Taylor series. Okay, you express ui at n plus 1 in terms of ui at the nth time step, previous time step. Okay, so you kind of land up with this particular equation, Taylor series equation. Okay, now you take dou u by dou t as minus dou f bar by dou x using this equation. Okay, so dou u by dou t I'll just substitute it. Okay, minus dou f bar by dou x, I have done that. Okay, similarly I have dou by dou t of dou u by dou t. Here what I do is that I will take the Jacobian form, minus a into dou u by dou x. I have put the minus outside. Okay, so then again we perform the same step. Okay, we have like dou by dou t of u, we again have it minus dou f bar by dou x. Okay, so that is why again it becomes plus here. Okay, so this way we come up with this equation and then we try to discretize it using a central difference scheme. Okay, so that is the way in which this is derived finally. Okay, so it is the procedure. For the details you can look at the slide. Okay, irregular structures will be, I think, covered in the last week or something. Yeah, so in general, I also try to work with irregular structures only. uh, See, there are two things. Structure is irregular, structure is irregular, but your grid can be regular only. Okay, so that we will anyway discuss, I think, in the last week also. But just to tell you, we can tackle with these codes. Okay, just to give a one word answer, yes we can. If we have a complex geometry, we can use quadrilateral cells only. But if we are going for unstructured grid which use this triangular kind of meshes, okay, all unstructured kind of stuff, if you are using these things are like very unstructured in nature, and it is we have to change everything, the discretization things. But once the this grid is quadrilateral of any shape, okay, we can handle. Okay, that I can tell you. This thing is not possible, this thing is possible. Okay, you can mail to me. Okay, we can look through that. I'll just recording this. I'll just stop the recording. Okay, so if you don't have any queries, you can leave the class. Okay.